Hey there, and welcome to this explainer. I am honestly so thrilled you're tuning in today because we've got a really exciting goal. We're going to completely demystify that heavy, complex machinery that powers your daily commute. We'll be breaking down the basic engine working model into what is essentially a highly synchronized mechanical ballet happening right under your hood. I mean, think about it for a second. What actually happens when you turn your car key or, press that push to start button? The engine hums to life, and it kind of thinks a bit like magic, right? But it's definitely not magic. It's actually the spark of a hidden, highly explosive mechanical world, and we're about to explore the whole shebang right now. Okay, let's quickly map out our journey. We're going to cover 1. What is a heat engine? 2. Meet the core components. 3. Essential engine terminologies. 4. The four-stroke cycle. And finally, 5. The synchronization matrix. So, part 1. What exactly is a heat engine? It's all about converting chemical energy to mechanical work. At its absolute most basic level, an automobile's engine is what we call a prime mover. It's basically a brilliant energy translator. It's designed to take the chemical energy stored securely in your fuel, transform it into thermal energy, or, well, heat, and then convert that heat into useful motion. Now, there are two primary ways we achieve this mechanical translation. On one side, we have the external combustion engine, or ECE. This is where the fuel burns outside the working cylinder. Think of a classic steam locomotive, right, where you're shoveling coal into a totally separate boiler. But on the flip side, we have the internal combustion engine, or ICE. Because the fuel burns directly inside the cylinder itself, ICEs are super compact, incredibly efficient, and they start up almost instantly. And honestly, that's exactly why they're the absolute standard for modern cars today. Moving right along to part 2, meet the core components. Think of these guys as the actors on our mechanical stage. Let's take a look at the stage and our key players. The engine cylinder, that's the stage itself. It's the absolute heart of the engine, and it has to withstand some pretty extreme pressures and seriously blistering temperatures. Then down below, you've got the crankshaft. That's the main rotating shaft that eventually delivers all that rotational torque right to your wheels. And up top, if you look closely, notice the inlet and exhaust valves. They act kind of like heavy spring-loaded doors, opening and closing to let vital gases in and out. So the really crucial point here is the intimate relationship between our lead actor, the piston, and its piston rings. The piston is this metal cylinder that reciprocates, basically moving back and forth, and it takes the direct, violent force of the combustion. But here's the catch. It absolutely needs those metallic rings slotted into its exterior to maintain a perfectly tight seal against the cylinder wall. Without them, high-pressure gas would just leak out, engine oil would seep in, and it would completely ruin the entire performance. No way around it. Okay, part 3, essential engine terminologies. Before we get moving, we've got to set our stage directions. First step, let's establish our ceiling. This is known as top dead center, or TDC. It's the absolute highest peak, the absolute upper limit that the piston can travel inside that cylinder before it literally has to stop and reverse its direction. And conversely, we have bottom dead center, or BDC. This is our floor. It's the absolute lowest extreme point the piston hits on its downward journey. The physical distance between TDC and BDC, that's what we call the stroke. So how does this all build into the math? Well, the swept volume, which we represent as VS, is simply the total volume of space displaced by the piston during one complete stroke, from that sealing up at TDC down to the floor at BDC. You calculate it using the cylinder's inner diameter, which engineers call the bore, or D, and the stroke length, L. All right, part 4, the four-stroke cycle. This is the main event. A standard four-stroke engine completes one full thermodynamic cycle through 4 very distinct movements. We've got suction, compression, power, and exhaust. What's absolutely vital to remember here is that these 4 individual piston strokes map out exactly 2 complete rotations of the crankshaft. That means it takes a full 720 degrees of mechanical rotation to get through one single cycle. Let's break those down. Stroke number 1 is suction, though a lot of folks call it intake. Try to picture blue arrows of fresh air rushing in. As the piston drops down from top dead center, it acts exactly like a medical syringe being pulled back. The inlet valve pops open, the physical volume inside the cylinder expands, and this low-pressure vacuum just pulls a fresh, perfectly mixed charge of air and atomized petrol right into the chamber. Then we hit stroke 2, compression. Now, that inlet valve slams shut. Both valves are completely sealed tight. Driven by the massive momentum of a heavy flywheel, the piston is forced back upward. It physically traps that fresh gaseous charge and forcefully squeezes it into a tiny little clearance space at the top of the cylinder. The pressure absolutely skyrockets, the temperature spikes, and the whole mixture enters a highly unstable state. It's just waiting to blow. Which brings us to stroke 3, power. This is the magic moment, right as that compressed mixture reaches its maximum density, an intense electrical spark from the spark plug fires. Boom! A rapid, violent chemical explosion goes off inside the cylinder. These violently expanding, burning gases literally slam into the head of the piston, forcing it downward with just massive pressure. Now get this, this downward push is the only stroke in the entire cycle that actually generates the mechanical power needed to rotate your wheels. And finally, we have stroke 4, exhaust. The explosive party's over, and we're left with the chamber completely full of smoke. The exhaust valve suddenly opens, and driven by inertia, the piston sweeps back up again. Picture gray smoke being physically swept and pushed straight out of the tailpipe by that rising piston. It clears out all the toxic waste and burnt gases, so the whole cycle can instantly restart. Which leads us to our final section, Part 5, the synchronization matrix. Let's look at the rhythm of the machine. Just notice how perfectly this rhythm aligns. The piston's direction, the open or close states of those valves, and the internal cylinder pressure, they all precisely coordinate across those 720 degrees of crank rotation. Like for example, you can see the pressure is actually below atmospheric pressure only during the first 180 degrees. That's the suction stroke drawing the air in. But then it hits its absolute maximum peak between 360 and 540 degrees during the power stroke. It's just a flawless, highly calculated sequence. So I want to leave you with this thought-provoking question. Can you imagine this precise, explosive, 720-degree, four-stroke ballet happening literally thousands of times a minute while you're simply driving to the grocery store? I mean, your engine might just be idling at 1,000 revolutions per minute. That means this violent, perfectly timed four-stroke sequence is firing hundreds of times every single second, completely silently, right under your hood. It is an absolutely stunning feat of everyday mechanical engineering. Thank you so much for joining me on this explainer. I really hope you walk away today with a newfound awe for the incredible science powering your daily commute. Keep learning, keep questioning, and I'll catch you next time.